Hello, my dear students, and welcome to a screencast and coverage of the next chapter, and that is chapter 7, which details with periodic properties of the elements and the periodic table. Now, I also must say that the important topic here is going to be periodic trends, and I'll make a few comments about it. I do love the way your book presents this material because two things. It doesn't overdo the periodic trends that you sometimes see in some books, exhaustive additional periodic properties, additional ionizations, other periodic trends that you can see. And it does relate these trends to the different groups of elements, also the major divisions within the table, metals and nonmetals. So that is less of what I'm going to emphasize. So I'll quickly go through the slides at the end. But Mendeleev is credited with developing and first introducing us to the periodic table. He was a chemist, but he was a chemistry teacher, and he developed this table so his students wouldn't have to memorize all the properties of the elements. I think there were 40 or 50 about the time he was doing it. And now, as we rewrite history and do so frequently, we try to give credit to other people who were developing some of the same ideas at the same time. I'm sorry I don't know more about Lothar Meyer, but he independently came to some of the same conclusions. Sometimes in some books you'll hear people talking about triplet rules and how groups of three elements shared similar properties, but he was developing an easy way to remember the elements and grouping them based on similar properties. And he saw that they fell into specific groups or families corresponding to our groups and families. Those mean the same thing. Those are the up and down rows in the periodic table. And one of the true values of Mendeleev's work is at the time there were gaps in the table, but it allowed for predictions to be made. And isn't that really what we want to do with science? To be able to predict what is going to happen in the future, or predict what is going to happen under these circumstances, or predict what is going to happen if we change this variable. And that's the real power of the periodic table, and these periodic trends reflect that power. So, a lot of people spend a lot of time on it. We'll just quickly cover this. We're really running out of time, so I don't know that I really wanted to do 2 more chapters, as I usually aspire to and usually get to half the time. So we're doing okay. I will see what else is going to come, and I need to, perhaps in a brief help session, talk about your final exam, which is coming up next week, although you may be seeing it sooner. And by next week, I'm assuming I don't get this posted until next Monday, which would be what, the 24th or so of April. I'll only give you a few questions to practice using these trends so that you can complete that assignment in a week and move on to the next chapter, the next material, or the final. So, making predictions, and excuse me, I'm suffering from some allergies, so I'll have to cough or take a sip of tea from time to time. This slide here shows us that there was an element missing, and Mendeleev, who grouped his elements based on atomic mass, predicted an element that they termed ecosilicon, and it was subsequently discovered. When they saw that something was missing, they went out looking for it, and when they looked for it, they found it. It was not difficult to find, and that's the element germanium. And it had the predicted properties, or properties similar to those predicted by Mendeleev's table. It fit between the two other elements and allowed for this prediction to be made. And if you hear ecosilicon or ecoluminum, those were the previous names for germanium and gallium. This is very powerful and allows us to make predictions, and allowed us to make predictions up until just a few years ago, when we knew what elements we wanted to make so that we could complete the periodic table out to 118. As I said, Mendeleev's table, being made in the 1800s, was based on atomic masses. It's what he knew. At the time, they didn't know about protons and electrons. They didn't know that the elements differ based on the number of protons in the nucleus, and therefore the atomic number. So now we'll see that. If you look down in the table around, for example, iodine, you'll see that the elements grouped by mass in several places would be out of order, because the most common isotope of a number of elements has more protons, not more protons, every element has one more proton than the previous one, but a previous one might have many more neutrons, making its atomic mass a little greater than the next one. So you cannot create a modern atomic table with all the elements in the proper order based on atomic mass. You have to use atomic number. And the modern tables do that. And when you look at those tables and you look at the properties of those elements and the order in which they're arranged, you see periodicity, repetitive patterns of properties for the elements. Briefly, I want to talk about sizes, especially of atoms, and I'll make just the some general comments about sizes of ions, ionization energy, and electron affinity, and then just briefly discuss these properties of some of the groups. We've discussed some of that before. So, one of the things that surprises people when we talk about size, atomic size, is that, if I don't know that I can go forward, is that when you look at atomic size, one of the things, well, let me go back. Oops. Having trouble going back, so let me do this and just enlarge this. When you look at size, as the elements get bigger and bigger and bigger and bigger and bigger, for example, down here on the row one up from the bottom, potassium, calcium, scandium, was that titanium, vanadium, chromium, manganese, you notice the numbers are going down. Even though these elements are larger and larger, the size is going down. Well, you wouldn't predict that, because look, why is that one bigger than the next one, even though it has fewer protons and fewer electrons. Well, there's a reason for that. And the reason is the nuclear charge. As the charge in the nucleus builds up, as you get more and more protons, more and more positive charge, it pulls those electrons in their orbits around them in closer because the negatively charged electrons are attracted to the positively charged nucleus. And as we get more charge interaction, those two sets of charges, the positive protons in the nucleus and the negative electrons in the electron shells, are drawn closer to one another. Effective nuclear charge is increasing. The nuclear charge is definitely increasing by 1 with every element as you go up the, in atomic number. But just because you have many, many protons doesn't mean that the electrons in the outermost shell feel that attractive charge because of something called shielding. The charge in the nucleus doesn't reach out to the electrons in the outermost valence shells because they're shielded by the electron shells interior to that outer shell. So, we are shielded. I will talk about the electrons repelling each other a little bit more as we talk through this. Remember, one of the reasons we pack them into these orbitals with defined geometric structures and shapes is our goal is to get them as far apart from one another as possible because they are repelling each other. But the electrons out here are not so attracted, not so attracted to the ones in the nucleus because there are electrons here shielding them. The negative charges out here being shielded from the positive charges in there by the clouds of negatively charged electrons. And so we don't always see the charge we expect. That nuclear charge is decreased because of this shielding we call S. And so you expect the charge to go up 1, 2, 3, 4, 5, 6, etc. But it doesn't. The nuclear charge does increase that. We'll call that Z. Remember, we have the Z number for our atomic number. But the effective nuclear charge that acts on the outermost electrons is decreased by screening. So you should know the term screening and effective nuclear charge. I won't give any problems doing these calculations. But we will see that as our atomic number goes up, our number of protons going across the period increases, and our effective nuclear charge is going to increase, right? More protons, even with shielding, greater charge. Acting on the electrons spinning around in their orbitals around that atom and around that atom's nucleus and drawing them in closer. Now, it's going to decrease down a group because why? Every energy level we get what? 1s, 2s, 3s. We get more and more orbitals that give us more and more shielding as we move away from the nucleus and move out. So it's going to decrease. Charge on this electron out here is going to decrease. And we'll see. The attraction, not the charge. The charge on the electron stays the same, of course. So, this just says and shows you graphically what I just said. As we go across a period, our nuclear charge increases. Certainly for the first couple of periods, but we are also going to see variation, for example, when you don't just plot the charge of the nucleus and the charge on the first electrons in red, but plot, for example, the forces acting on the valence electrons. And you can see some differences when we drop from the first period to the second period. Okay? So, well, actually, the second to the third. Okay? Oops, I should do it this way. Second and third. Okay? So we start over. We had lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Then we go sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon in the third period. And you can see also a drop when we went and moved out to another period in energy level and other orbitals. So, one of the things we have to do is tell you, when we look at the size and we tell you the size, the atomic dimensions of an atom, we don't put on our Superman glasses and get a ruler and just measure that atom. These dimensions were originally measured by measuring the size of a molecule and the distance between two of them. For example, in diatomic molecules like oxygen or fluorine or nitrogen. And when we did that, we could measure an atomic distance, a bonding distance, if you will, although they make it clear it's a non-bonding atomic radius or van der Waals radius, about them. And while you can measure that distance with, fairly sophisticated, but they've been around for a long time, spectroscopic techniques, you see this distance, and the assumption is that the atomic dimensions, or the radius, and then you can do not just d for distance between the two nuclei, but the diameter, because that's something else you might see reported. So you have radius, and then you have diameter. That can be calculated from the bonding distance between these two atoms bonded to each other. And technically, they didn't measure the size of the atom. They measured the distance between two nuclei of two adjacently bonded atoms and divided it by 2. So just a technicality. So when we talk about size of atoms and the atomic radius, that's how it was done. They didn't measure it directly, but it's calculated, and it's calculated very accurately. And if I can't really make this bigger without doing that. This distance here, oops, I'm not writing on it anymore. This distance here is the radius, okay? And if you see, you'll see as you go left to right across the period, it's decreasing. Magnesium is smaller than sodium. Boron is smaller than magnesium. Carbon smaller than boron. Nitrogen smaller than carbon. Oxygen smaller. It's decreasing. Even though those atoms are increasing in atomic number, increasing in number of protons, increasing in number of electrons, they are getting smaller left to right across the period. And that might be a little counterintuitive. But as we said, the reason is the effective nuclear charge is increasing across that period and providing greater attractive force between the electrons and the orbitals and the nucleus, positive charge in the nucleus, and pulling them in closer together. So it does make sense when you understand a little atomic structure. Of course, the sizes increase as we go down a group or a family. For example, in group 1, we have hydrogen, lithium, sodium, potassium, rubidium, who's next? Cesium. Anyway, it's increasing as you go down. Well, that's because, of course, you keep getting additional shells. 1s, 2s, 3s, 4s. Just thinking about the first group, 1s1, 2s1, 3s1, 3s, 4s1. Those elements, as we go down the group, of course, get bigger from top to bottom because they're adding additional orbitals. Now, if I may just quickly tell you about ions. In general, they follow the same trends, decreasing in size left to right, but with some important exceptions, and that is, as we go from, let me increase this again and see if I can help you make a little sense of this. Let's do the anions first, the negatively charged anions. And it's not letting me write. In these negatively charged anions, if you look, I've got oxygen there, and O2 minus is even bigger. Fluorine is here, and F minus is even bigger. You might say, well, that makes sense because I added an electron. I have more stuff. And that is the case. You have more negative charge that needs to be accommodated, and it spreads everybody out. Okay? We want to be as far apart from one another as possible. So my elemental form is smaller, and my ionic form is bigger because I have more electrons I need to spread out. Now, that's true for anions. Okay? For negatively charged anions. For your cations, for your positively charged cations, they get smaller. And that might make sense if you say, well, they lost something. They lost an electron. But what they really lost was the charge on that electron, so the remaining electrons didn't have to spread out so much. And the other thing is, in these group 1s, they had a single valence electron, and when they lost it, they went down to the previous shell. So they not only lost an electron, they lost a whole valence shell because, lithium was 2s1, and it went back to, 1s2. It was 1s2, 2s1. When it loses that electron, it becomes that. Okay? Sodium was 1s2, 2s2, 2p6, 3s1. Well, it lost this s electron, and that's a 6, not a G. And so it goes down. It lost the third energy, the orbital on the third energy level, and went down to orbitals only in the second energy level. So, of course, it got smaller. Similarly, magnesium, which was 3s2, loses 2 electrons, and when it does that, it gets much smaller. And it's even smaller than sodium. Why? Because it has more protons, one more, that draws the remaining electrons in closer, and there are fewer of them. So, actually, they're the same number because those are what we call an isoelectric species. Let me move on and talk about isoelectric species. As we go through an isoelectric species with the same number of electrons, but with increasing numbers of protons, then, well, not necessarily in every case here, but obviously oxygen and fluorine minus. Oxygen is group 6. It has 6 electrons in its outermost shell. It wants to have 8, so it picks up 2 electrons, a negatively charged. But fluorine, the next element over with 1 more proton, also, it has 7 electrons. It wants to have 8, so it picks up a single 1, so it can have 8 electrons in its outermost shell. These two are what we call isoelectronic, but the fluorine has 1 more proton. So it has a higher nuclear charge, a higher positive charge in the center to pull everybody in closer, and it has a smaller atomic size. That just explains some of the reasoning behind it. The main thing I want you to remember is that anions are bigger and cations are smaller. Now, there is this term called ionization energy. I like to really drive this home with a lab and some plotting. So we'll just cover it quickly and have you prepared for a lab when that day should come. The ionization energy is how much energy is required to remove an electron from an atom in its gaseous state. And the first ionization energy is the energy required to move the first electron. The second ionization is the energy required to move the second electron. The third ionization energy is the energy required to remove the third electron. And there can be major differences based on position in the periodic table and how many electrons you have to remove. For example, if you are group 1, you will remove the first electron relatively easily. If you are group 2, you'll remove the first one relatively easy, but you'll remove the second one, relatively easily too. I'm looking at the example here, but in a group 1 element, removing the first one is relatively easy, but removing the second one is hard. Because when you remove this one and made sodium plus, now it has 8 electrons and it's happy again. Sodium, I'm in the wrong period, but now it has a noble gas configuration. If you make this very unusual species, it requires a lot of energy to strip that second electron out and make this sodium 2 plus species. So it just depends on where you are. But in general, it requires more energy to remove a successive electron, but sometimes it takes a lot more. Magnesium, for example, gives up its electron, and it gives up it to form magnesium 1 plus, but it gives up its other electron to form the more common magnesium 2 plus species, like that. So, I will apologize. There may be some noise in the background while my family moves about the rest of the house. But these ionization energies, sodium element number 11 loses an electron, becomes 10, but what's special about that 10? That sodium ions is 1s2, 2s2, 2p6. And if you look, that adds up to 10 electrons. Because normally it would be what? 3s1, but it loses that one. But to lose one of these electrons in its p orbitals takes an enormous amount of energy. As you see there, it goes to almost 4,000. And that is a really large difference compared to magnesium, which required, more, as it said, more energy, because we have a higher effective nuclear charge. It's attracted more strongly, so it takes more energy as we move over one to magnesium. But magnesium's pretty happy to give up its second one, too. It still requires more, because it's got one more proton and is more strongly is the term, attracted, but it does relatively easily give it up so it can form the typical magnesium 2 plus. And we're talking 1,400 versus 4,000, 4,500. Those values. And those are in kilojoules per mole, but we're not going to be doing any of those calculations at this point. But let's talk about the trend. Increases across the period and decreases down a group. Why does it decrease down a group? Because when you want to pull out that first electron, it's further away from the nucleus. That charge attraction, that force decreases with the square of the distance. So a little bit of distance really greatly decreases the force and makes it that much easier to remove those electrons. So it decreases down a group and increases across a period. Where people get confused is looking at exceptions or big and small jumps based on electron filling, and the fact that we rephrase this very easily. The first ionization energy doesn't just increase across the period as you go left to right. You can phrase it decreases across the period as you go right to left. And I used to hate this. Most of the books are pretty good now, and your book is very good. But the first ionization energy, generally increases as you go up a group. And depending on which electrons you're talking about, you can see some differences. But as they say, there are exceptions, so we say generally increases, for example, as you move across a D block. So that's ionization energy. Smaller atoms have higher values of first ionization energy, and that makes sense because the electrons are close to the nucleus. Let's see, factors that influence. We'll just leave it at that, but it all really relates back to this term of the nuclear charge, the number of protons, which, by the way, equals the nuclear charge. each proton having a value of +1. Okay, +1 charge. And then we allow for shielding when we calculate that. I already talked briefly about this. Trends may not be followed. For example, when we go from nitrogen to oxygen, we have 2p1, 2p2, 2p3, and we fill up the px, py, and pz that we talked about, orbitals. And we fill them up successively. We don't, for example, put for P1, put it in the PX1, and P2, put the second one, but with opposite spin, in the PX, and then do this for P3. No, we go one in each orbital. We want them as far apart as possible. They repel. And then when we have to, we fit the second one in. Or not the second one in an individual suborbital, but not, this would actually be what? Our fourth, our fifth, and then our sixth. So oxygen, you're not talking about electrons in equivalent orbitals. You're talking about two in one orbital. And this oxygen, if you remove one of these, would have this configuration, which might be more stable. So you'll expect some variation there. So we've already talked about the ions and what happens when you change them. If you're losing an electron from not just an orbital, but an energy level, to give you a stable configuration, that jump is going to be a smaller jump and a more permitted jump. Okay? So let's talk about electron affinity. Certain atoms have a very high electron affinity, and I'm going to equate that with a term called electronegativity. The electron affinity is the energy required to add an electron. So different from ionization energy, even though we're making an ion, we're adding an electron, not removing an electron from an element. And some atoms love to accept electrons. For example, chlorine. Okay, it's group 7. It has 7 electrons in its outermost shell. Wants to have 8. It doesn't, it wants that electron very much. In fact, this is more stable at a lower energy level than this, and thus it is an exothermic reaction, and our value is negative. Okay? And so chlorine is an extremely, what we call, electronegative atom, or it has a very high electron affinity. I will show you a simple way to kind of remember this and simplify things that will allow you to answer the questions. It says not much change in a group, and that's true, because all of the ones, along with chlorine in group 7, have 7 electrons, and they all want to have 8. And so if you give them an electron, they will assume a more stable noble gas configuration in their outermost shells, and as a result, their values are negative with a large release of energy, all around 300, 328, 349, 325, 295. You don't see, like it says, not much change within a group. And the trend here, it goes up, then back down to bromine, then back down to iodine. So we won't make any generalizations about that. I will say some people like to talk about that value, but what I like to do is talk about electronegativity. I'll show you a table when I do the help session for this set of questions. But to put it simply, fluorine is the most electronegative element. And these electronegativities are going to become important when we use them to discuss bonding and the difference between ionic versus covalent bonding and polar versus nonpolar covalent bonding. But this is the most electronegative atom, and the closer you are to fluorine, the more electronegative you are. So electronegativity increases this way. To me, that simplifies it. Rather than looking for trends in this, fluorine's the most electronegative atom, and the closer you are to it, the more electronegative you are. So electronegativity is going to increase bottom to top and increase left to right. People get confused about saying it decreases top to bottom or increases bottom to top, etc. But I want to talk about that term electronegativity when I give you a couple questions to answer. Let's talk about those periodic properties and those trends in terms of the periodic table and groups and reactivity and properties, not reactivity, but all reactivity and other properties within a group. Metals, about 70% of the periodic table are on the left-hand side. They have an abundance of electrons. They have low ionization energies because they give up their electrons easily because they have so many. We talked about that with metallic bonding and the like. And we view that a metal is a bunch of nuclei floating in a sea of electrons. And then he also explains why they have those extra electrons that are relatively mobile and relatively free or easily displaced. That allows it to carry a current. Okay, makes them good conductors. The nonmetals, of course, are the opposite. They tend not to carry a current. They tend to form anions or negatively charged species. They like to take up electrons. They don't like to give electrons off. They don't have any extras to give. These all tend to form, of course, the metals all tend to form cations and be positively charged. The anions tend to be negatively charged. They tend to be poor conductors. And then, of course, in between the metals and the nonmetals, we have the metalloids along this stair-step division that you see on every periodic table. And they're not good conductors. They're not good insulators. They're not good conductors. They're not bad conductors. They're semiconductors. Notable things like silicone, which is often doped with arsenic and germanium and tellurium, etc. So, I've already talked about this. Metals have plenty of electrons, so they're always willing to give them up, and they tend to form cations. Nonmetals tend to form anions. That said, metals are very ductile, very what? Ductile means able to be pulled into long wires, and they're very malleable, which also means being able to be pressed or formed into thin sheets. You can form sheets of gold. I have some I like to pass around. They're only a few atoms thick. Rutherford took advantage of that in his famous gold foil experiment. And so very, very malleable because they're this sea of electrons that you can squish and draw out, even though they're solid, and make them mold to what you want them to be. They're all solids at room temperature except for mercury, one of two liquids in our periodic table, and low ionization energies. What does that mean? It means they form cations. It's easy to remove those electrons. Their reactions are show some similarities. Okay, they tend to form ionic compounds. Their oxides tend to be basic. Whatever. We'll talk about some of them that react specific ways. Nonmetals, like we said, are dull, brittle, poor conductors in general, tend to be. Very large electronegativity, okay? That means very good electron affinity. They love to form anions, take up electrons, and they're happier and at a lower energy state when that happens. So we have negative delta G's, or the thermodynamics of that is such that it is an exothermic reaction when it happens. They tend to form molecular compounds, covalent compounds, and here's your summary of the two. So, metalloids, like we say, have some of the properties of both. They make great computer chips, and within the elements of the periodic table, when we group them into groups as Mendeleev did, we see similar chemical properties. There are trends for other properties like density. You could even put reactivity in there. Alkali metals are soft. You tend to be able to cut them with a knife. They're so reactive you don't find them in their pure state in nature. In fact, there aren't very many elements you do find in their pure state in nature. Some, very notable, prominent ones. Gold is found in the pure state. I guess you can find copper and magnesium nodules in the right place. Of course, oxygen and nitrogen are present in our atmosphere in their pure state. When you find a diamond or graphite, it's pure carbon. But, I can't really think of a lot of other elements, especially metals, that you can find in the pure state. So they tend to be very reactive. These alkali metals especially are called that because when they are dissolved in water, they react with water very violently to form an alkaline basic solution. They take the hydrogen from the water to form explosive hydrogen gas, not explosive hydrogen gas, but hydrogen gas that burns. And then they react very violently at a high temperature all at once to strip that hydrogen off. You have two of them. You form what? H2 plus OH minus, the base, the basic alkaline hydroxide species. That's where it comes from. The alkaline earth metals do much the same thing, although they don't react so strongly with water. Sometimes it has to be steam or hot water, but they are common in the Earth's crust, so they're called the alkaline earth metal. So they like to form oxides. They give characteristic flame test. I want to stop and talk about this, and then we're done. Lithium is a beautiful crimson scarlet color. Sodium is orange. You wouldn't notice it's different much from the orange flame. Potassium gives a beautiful purple color. I'm from Texas, and we do mesquite barbecue. Mesquite wood is known for concentrating potassium ions and glowing with a purple glow in the campfire. Very beautiful. This and the other colors corresponds to electrons being what? Elevated to a higher energy level, to a higher orbital. Because of the heat, you can do that. You can excite electrons with everything from friction to heat to electricity. And in a chemical reaction, uh, you can even do it, a chemical reaction biologically. So we have bioluminescence and chemiluminescence and triboluminescence. But heat and electricity, heat in a flame test and electricity in a electrical discharge tube are great ways to excite electrons. And remember, they're excited to specific energy levels, and they do, because of the quantized atom, very specific energy transitions. And when they fall back down to ground state, or where they're supposed to be, they shed that excess energy as heat and light. And the light, those are very specific energies, and therefore the light is at a very specific wavelength, some of which we can see, and some of which, some reactions or some excitations and subsequent decays that are more common that give us very specific colors. And people still do flame ionization detection to determine what metals are present in a sample, although mass spectrometry and other spectroscopic methods give them more detail. The alkaline earth metals, like I said, are similar, but not quite as reactive. Some different properties, but more common in the Earth's crust. Of course, I don't know, if we get much more than this chart. The group 6, also called chalcogens in the old days, oxygen, sulfur, and then becoming increasing metallic, selenium, tellurium, and polonium. Selenium is what's in Selsun blue, and selenium, Selsun blue, and Head and Shoulders. Inhibits pittosporum ovale, a fungus that contributes to inflammation in the scalp and rapid skin growth and dandruff. So, interesting properties for some of these. You might have a Kia. Is it Kia or Nissan? Somebody makes a Telluride, which would be what? The anion of tellurium. Car these days, named after Telluride, Colorado. I suppose it's an SUV or pickup style car because it implies toughness. But the halogens in group 7 all form -1 ions and react very easily with metals to form metal halides. Sodium chloride, sodium bromide, sodium iodide, sodium fluoride, all common compounds that you see in life, but also with other metals, magnesium chloride, potassium bromide, potassium iodide, all kinds of metal halides form, and because these react very easily and are common. So lots of our salts tend to be these halide salts that we deal with in the lab and in our lives. And of course, the noble gases have the stable noble gas configuration, and being very stable, have very large ionization energies because they do not want to react. We can play some games in the lab and make some compounds with these gases, which are just not just inert, but they're actually noble, because historically they never formed any compounds with anything, and they are I would say completely unreactive except under exceptional cases. And they're also all monatomic. They don't even react with themselves. And they also don't even want to interact using weak forces, van der Waals forces, and the like. And so they do not form liquids very well. Their boiling points are many hundreds of degrees, even when they get very large, below freezing. Okay? Remember, 0 degrees is 273 K. So these guys are, for example, helium and neon and argon, hundreds of degrees, or 100 degrees, or half 100 degrees for radon. But they do not even form liquids very well. They don't want to react or interact with anybody or anything, even themselves. That's it. I will post a quick exercise for you to do. And there'll be, of course, we're coming up on the final 2 weeks of the course. I've decided to make the final an assessment, just like these chapter assessments, that will be taken from the old chapters with just the values changed. And until I post either the next chapter, I'm not sure I'm going to do the next 2 chapters like I really want to, or our video help session, please, many of you need to catch up and get all your work in and get that in, because it's crunch time now. I'll give you the time we have, but we don't have a lot of time left. So please focus on chemistry in these coming 2 weeks and get this course completed and your work completed and this course out of the way so you can get your course credit. So until the next time you hear from me or I have a chance to talk to you all, please stay safe and take some time to focus on chemistry. Goodbye now.